In the lab project manual, we had a section roughly on page 134 entitled More Latch, Unlatch Logic. And if you look at the code right here in front of you, this is what we had when we finished the last lab. In this lab, I told you to set input 0 and input 1 on and input 2 off, just as you see there. And then the question was, do you see any unexpected behavior or unwanted behavior? Well, we're right back to where we were with two instructions addressing the same bit in memory as far as executing against it. Both these rungs are true, so this rung is true, so it turns on bit 0. This rung is true, so it turns off bit 0. We're back to the scan-dependent logic, and in order to eliminate this, we're going to do something that's very commonly done in logic for many other reasons, not just for this. For this is really not a situation that you would program on purpose. So to prevent this, we're going to put both of these rungs into the edit mode, and to each one we're going to add a true if off. And then we're going to take the address of one and the other. So we basically end up with logic that will make it impossible for both rungs to be true at the same time. That doesn't mean that you don't get some interesting results. But notice if both of these are on, neither rung is true. Or if both are off, neither rung is true. Okay, both inputs are on. With both the inputs on, do you see the same intermittent behavior that you witnessed before? No. Why? Because we have added permissives or conditions in each rung that makes it impossible for both rungs to be true at the same time. Turn input 0 off and input 1 off. Okay, they're both off now. Are either of the outputs, output 0 or output 2, on? No. Turn input 1 on and then input. Now you got to do it in that exact order. Turn input 1 on, then input 0. Are either of the outputs, output 0 or output 2, on? No, they're not. Neither rung is true. That was one possible sequence for changing the state of the inputs. Let's try a slightly different one. Watch carefully and be thinking about what you are doing in each step. Now think about what we did the first time. We had them both on. If I turn, well, both inputs were on just like they are right now. Neither rung is true. If we turn input 0 off, this will be true. That would unlatch the bit, but the bit's already off. So in that sequence, we went both on and both off, and these stayed off. Now in the next sequence, we're going to turn input 1 off. Now doing it in that order, with input 0 on and input 1 off, then it latches that bit. And the question was, are either of the outputs, output 0 or output 2, on? Yes, they are. In the first sequence, we started with both inputs on. Then we had you turn input 0 off, then input 1 off. We switched the state. When these were both true, it said to turn off bit 0, but bit 0 was already off, so you saw no change. Then turn input 1 on, and then input 0. And again, because of the order, in other words, this rung was true, but this rung was never true. Rung 0 was never true in that first sequence. Now we're going to turn input 1 off and then input 0 off. Because this rung was true before it went false, we set the bit. Now we're going to turn input 0 on, then input 1 on. And see it stayed on. Think about the sequence that you toggle these inputs. In one case, the only rung that was true was rung 1, which turned the bit off, and the bit was already off, so you never saw it go on. Compare your answers in the first pair of questions with the second pair. Why are they not the same? And that's because of the sequence that you executed. Save your project and go offline with it. So we're going to save as, we'll just save it. We already have it named. Go offline, and we had you open up this instruction and type in an O, and then we had you go up to this instruction, type in a C. So now we have two examine-ons or true-if-ons to control setting the bit, and two examine-offs to control resetting the bit. Before we edited the logic, we had two unique memory locations, local 1i data 0 and local 1i data 1, as the conditions or permissives for determining the true or false state of rungs 0 and 1. One condition to set local 1o data 0 to on, and another condition to set local 1o data 0 to off. Both conditions were of the true-if-on type. It is the fact that the instructions is true that executes the OTL latch instruction or the OTU unlatch instruction, and not specifically whether or not that bit was on in memory. A true-if-off is true if it addresses a bit in memory that is off. Remember these two instructions, true-if-on, true-if-off, or XIC and XIO, that they are queries. When we say that they address bits in memory, the true-if-on instruction queries that bit in memory, and if that bit is on, then that instruction is true. The true-if-off instruction, it queries that bit in memory, and if that bit is off, then the instruction is true. True-if-on, true-if-off. Let's take a brief look at the circuitry to clarify the effect of that change in the instruction type. Remember that pushing a button does not always turn something on. We tend to think of pushing a button and it turns something on. You can push a button and it turns something off. If you use a normally closed contact, the contact's closed when no one's touching the button. You push on the button, the contact opens, and you break power to the circuit. There's an illustration on page 138 or so in the manual, and that's what we're discussing now. So if you don't have the manual in front of you, you need to go get it, pause, go get your manual, go to page 138 or so and find that diagram. In that diagram, we have an abbreviated circuit representation. Syncing and sourcing is not relevant in this diagram. If you wanted to make that dashed line an electrical connection with no electronics in between, then this would not work out for syncing and sourcing. That dashed line represents additional electronics. It is assumed, of course, that the controller is in a state that is updating the I/O to and from memory, which means it's in the run mode. We have a normally closed contact push button labeled stop and a normally open push button labeled start. They are connected to inputs IN0 and IN1 on an input module. Voltage type and level is irrelevant at this point. The circuitry that transfers the state of the optical isolator via the backplane to the associated bit in the controller's memory is represented by a dashed line. Likewise, the state of the bit in memory associated with an output device, like OUT0, is connected to an output module. Although voltage is applied to everything, only completed circuits are conducting and represented with green lines. Are there any completed circuits in the field wiring? Yes, there is. Which? Well, input 0 is a normally closed push button, the stop push button. So there is current flowing through that opto-isolator marked IN0, which turns its associated bit on in memory. Are there any bits in the on one state in memory locations connected to devices in the field wiring? Yes, there is. Which one? Local 1i data .0 or IN00, whichever you're actually using. Just so you're not confused, the nomenclature next to the input bits says local 1i data. That represents the whole word, not just those 6 bits. But since we're only using 6 inputs and 4 outputs, that's all we have to somewhat declutter our drawing. Relate the state of the bits in memory with the action of depressing one of the push buttons. Depressing the start push button does what to its bit in memory? Turns it on. Does depressing the stop push button does what to its bit in memory? Turns it off, because it's a normally closed that was already on. So when you push the button, that bit in memory goes off. If you look at the diagram, you'll see that bit 0 of that data word right now is on. There's a green 1 in that position 0, and that's connected to input 0. Trace the electrical path action from the input field devices to the output field devices. Is it continuous? You could answer yes or no. Now, I said electrical path action from the input field devices to the output field devices. So it would determine, your answer could be either based on what your perception is of the question. I will admit the question does leave a little bit to be desired. If there is a break or gap, where is it? Well, there's actually a couple. There's an optoisolator that electrically isolates the field wiring from the backplane. And then the bits in memory in local 1i data that are controlled by the input field devices, so to speak, they are isolated from local 1o data, and those bits that control the output devices, they're isolated by the logic. If there's no logic between the two, then there is no path or action from the input field devices through the input memory image to the output memory image. Then, if there were in local 1o data, output 0, it goes out to the optoisolator. Then once again, there is electrical isolation between the LED in that optoisolator and the optical transistor that actually controls the output device. What bridges the gap? Well, light bridges the gap for both of the optoisolators, and logic bridges the gap between the input image and the output image. Why would we want to use a normally closed push button to stop a device? It is referred to as fail-safe. With a normally open contact or push button, if the wiring fails, which would mean open, you won't know it until you push the button or close the contact to stop the device, and it just does not stop. Because when you push the button, there's a break in the wiring, so you may close the contact, but the circuit's still open. That's why we use normally closed. With a normally closed push button or contact, if the wiring fails, the device stops instantly or won't even start and will not run until you fix the circuit. It fails into a safe condition, no motion. You might say that it is okay to run the device if the stop bit in memory is on. Consequently, if we want to stop that device, we must set that memory location to 0 or off. In the manual it says, online with your project in the remote run mode and local 1o data .0 in the off state, which you see it's not here. Input 0 off, which you see is the case, and input 1 on, again the case that you see here. If you do not follow the sequence exactly, you will have to start here again in this step. I want this bit off, so I left it like this so I could remind you how to do that. Right click, toggle. So whatever state it's in, a single toggle toggles it to the other state. So if you want to go off and back on, that's 2 toggles. A toggle is one single state change to change it to the opposite of what it is at the time you toggle it. Now this action does not specifically turn it on or turn it off. It toggles whatever state it is in to the opposite state. So again, if you desire to turn it off and then on, that requires 2 toggle. Local 10 data.0 should be off, which it is. You can see in front of you. And my logic on the screen in the run mode matches what is in the manual on roughly page 140 or so. Are any of the bits that are addressed here in this illustration in the on or one state in memory? Yes, if any. Which? Local 1i data 1. So bit 1 of that data word is on. And it's on because that switch is on. Are either of the rungs, or is either of the rungs of logic true? No, none of them are true. While observing the rungs of logic and the state of the instructions, toggle input 1 off. Now notice that when we did that, the output 0 is off. When I turn output 1 off, nothing happens other than the state of that bit in memory changes, and now rung number 1 is true. Are any of the bits that are addressed here in this illustration in the on or one state in memory? Look closely. No, none of them are on. Look at the top rung. Input 0 and input 1, they're both off, and so is the output. Data local 1 O for output, data 0. They're all off. While observing the rungs of logic and the state of the instructions, toggle input 1 on. Are any of the bits that are addressed here in this illustration, in front of you, this logic, in the on or one state memory? Yes. Local 1i data.1. That switch is on. Is either of the rungs of logic true? No. Did this action, when true if on input 1 went true, change the state of the output bit, local 10 data 0? No. Why? Because it was already off, and when we made rung 1 true, it was telling output 0 to be off, but it was already off, so it didn't change its state. When you have a rung that is true, and it's working with an OTE or an OTL OTU, that true rung is executing every single program scan. If we look at our monitor for the main program and we go to Properties, Monitor, we're running at about 20 microseconds per scan, which means every 20 microseconds, this rung right here, and this one only, is telling that bit memory you're off. 20 microseconds, every 20 microseconds. That's thousands of times per second. This logic is telling that bit you're off, you're off, you're off, you're off, you're off, you're off. These 2 rungs up here, they're saying nothing. This has a false execution. When it's false, it tells that bit in memory that it addresses you're off. These do not have false executions. These rungs are not telling those bits that they're off or telling them that they're on if the rungs were true. Now, if this rung were true, then it would be saying you're off, you're off, you're off thousands of times a second. If this rung were true, then it would be saying you're on, you're on, you're on thousands of times per second. However, with a latch instruction or an unlatch, once you've set it, you don't need to keep repeating it. But nonetheless, the logic over here does not know what these instructions are. You got, this is false, so you have a false out, true, but you don't have a true out here because this was false. But if this rung were true, then every 20 microseconds, you have a true out. It doesn't know what instruction's over here. So it doesn't know that it doesn't need to keep repeating, you're off, you're off, you're off, or you're on, you're on, you're on. The last question was, did this action, when true if on input 1 went true, change the state of the output bit local 10 data.0? No, it did not. Why? Because it was already off. While observing the rungs of logic and the state of the instructions, toggle input 1 off and then input 0 on. And you could ask the same questions. Are any of the bits that are addressed here in this illustration in the on state in memory? Yes. Input 0. Is either of the rungs of logic true? No. Why didn't that last action turn on output 0, local 10 data 0? That's because it's the order that we did it in. Remember? We toggled input 1 off first, then input 0 on. If we'd have done it the other way around, we may have gotten a different reaction. While observing the rungs of logic and the state of the instructions, toggle input 0 off. Now that rung is true, but local 10 data 0 is already off, so you don't see any change. We toggle input 0 off and then input 1 on, followed by toggling input 0 to the on state in that exact order. Now we have a bit on in memory. Are any of the bits that are addressed here in this illustration in the on or 1 state in memory? Yes. If any, which? Local 1i data 0, local 1i data 1, and local 10 data 0. Did this action, when rung number 1 went true, change the state of the output bit local 10 data 0? Yes, it did. Why? Because the rung went true, and rung 1 is not also true. If it were, then last man would win. It would be off. While observing the rungs of logic and the state of the instructions, toggle input 0 off. Are any of the bits that are addressed here in this illustration in the on or 1 state in memory? Yes. If any, which? Local 1i for input data 1 and local 10 for output data 0. Is either of the rungs of logic true? No, neither rung of logic is true. Remember, the key here is that the latch and unlatch instructions, OTL OTU, do not have a false execution. So when the rung goes false, nothing changes. It means nothing. While observing the rungs of logic and the state of the instructions, toggle input 0 on. Is either of the rungs of logic true? Yes. Rung 0. Did this action, when rung 0 went true, change the state of the output bit local 10 data 0? No, it did not. Why? Because that bit was already on, and this rung going true, the previous scan, it was saying nothing because there's no false execution. When this rung was false, it says nothing to that bit in memory. When it's true, it says you're on. So this rung can go on and off continuously, and that bit will stay on continuously forever until some other instruction, like this one, that rung goes true and sets it back to 0. While observing the rungs of logic and the state of these instructions, toggle both input 0 and 1 to the off state. Is either of the rungs true? Yes. Rung number 1. Did this action, when rung number 1 went true, change the state of the output bit local 10 data 0? Yes, it did. Why? Because when that rung was true, now it's telling that bit in memory, you're off, you're off, you're off. Remember, this rung right now is saying nothing. It's silent. This instruction is silent when the rung is false. Well, both of these instructions are. But this instruction and this one aren't silent when the rungs are true. This one says you're on, this one says you're off. This rung is true, so it's saying local 10 data 0, you're off, you're off, you're off. Sit down, sit down, sit down, thousands of times a second. It's important that you know that, because when you start doing fairly convoluted logic, that may bite you in the butt if you don't keep in mind that these two instructions do not have false executions. They only have true executions. This one has a true and a false execution. We did repeat one sequence to emphasize that it is the order that you sequence those two input states that determines the state of local 10 data 0, and not just which inputs are on in any given instance. In the manual, I had two diagrams for you to compare. In both cases, the rungs are both false, but one indicates that local 10 data 0 is in the on state and the other is in the off state. Those two diagrams show you conclusively that the logic can show the same state but have the opposite state for the outputs. That's important to know for troubleshooting. And then we had you do just the opposite and compare those against the previous two. In the manual, we have 3 pairs of the same code. They're marked 1, 2, 3, 4, 5, 6. And I had you compare all those. Then I said, how many combinations of the rung conditions can exist that show the state of local 10 data 0 in the off condition? And there were 3 of them. 3 separate conditions that shows bit 0 off when input 0 is on and input 1 is off. That's in the first pair, 1 and 2. And then in the second pair, 3 and 4, you see in number 3 that those 2 now are false, but the second 2 are true. And yet local 10 data 0 is off. And then in the third pair, 5 and 6, you see number 6 that it shows the output off. For the 6 states shown above and on the previous page, identify which rung, 0 or 1, had to be true last to leave the memory locations in their displayed state. Now you're going to have to think about this very closely. Well, the answer was really easy to figure out. If the pair has data 0 off, then you're going to have one answer. If it has it on, then you're going to have a different address. So for pair number 1, rung number 1 had to be true last. For pair number 2, rung 0 had to be true last, because in pair number 2, output data 0 is on. Pair number 3, rung 1 had to be true last. In pair number 4, rung 0 was true last. And just so you didn't grab a pattern and just start filling in the blanks, I switched it up. Pair 5, rung 0 was true last, and in pair 6, rung 1 was true last. If you don't have this concept down solid, do not proceed into the next lab until you do. Go back and do these labs over and play with this code. It's right in front of you. So try different sequences of the order that you turn the bits on and off, the rungs that are, what rung is true last. If you look at what's there right now, I can turn on 0. That does not change the state. Really, you don't know which occurred first between these two. But because that's off, you know that this could not have been true last. Because if we turn that on, see, now those bits are on. If I turn that back off, they're still on. So this is the exact same static conditions, but shows 2 different states for the output bit. So you need to really understand how this logic works, because this is a fundamental underpinning of writing ladder logic diagrams, especially reading them and troubleshooting. Often I've thought it's easier to write programs than it is troubleshoot, because you can write something, you can write a paragraph, write a letter to someone, write a note, and you know exactly what it means because you were the one thinking when you wrote it. However, the person that reads it may not get the same idea that you had. That depends on how good of a communicator you are, how good your grammar is, and your mastery of the different parts of speech, like verbs, adverbs, adjectives, nouns, pronouns, prepositions, etc. You really have to understand code really well to be a good troubleshooter. That's why you see people that sit in a cubicle and write code and then send it to someone else to commission it, to finish it. Sometimes it's pretty light in the area of completeness, and it takes a lot of work to get it working.